let me remind you of the definition of a group. So we said that a group is a set, we'll call the set G, with a binary operation. That means a binary operation that takes two elements, and we sort of multiply them or add them together to get a single element. And then we have three axioms: associativity, identity, and inverses. And maybe I'll just say them in words. Associativity is if you reverse the order of parentheses, then the outcome of multiplication or addition will be the same. Identity means we have a 0 or 1 element, depending on if we're thinking about addition or multiplication. And every element has an inverse, which we can multiply / add in order to get the identity element. Okay, now I want to extend this definition to subsets of the set G. And the concept that we're looking for is called a subgroup. So a subgroup is, well, it's a subset of G, which is also a group. Also a group in its own right. So as an example of this, let's consider the group. Let's consider the group G. Let's call it G, and let's consider the group C6. That's the cyclic group with 6 elements, which is just those 6 elements. I'll write them multiplicatively, so we can write 1x, x squared, x cubed, x to the 4th, x to the 5th, now we just go back to the identity because there are 6 elements. Here we are. And I want to find a subset of this set that is a group in its own right. And the subset that I'm going to choose is the set containing 1, x squared, and x to the 4th. So let's call it H, maybe. H is set 1, x squared, x to the 4th. So how do I check if this is a subgroup? So what I need to do is I need to check these 3 axioms. So associativity. Well, multiplication in H is really the same as multiplication in G. So associativity, I know from G. Identity, yes, H has an element that's the identity, and the inverses. So in the group C6, x squared times x to the 4th is x to the 6th, which is 1. So x squared is the inverse of x to the 4th, and vice versa. So each element here, 1x and x to the 4th, 1x squared and x to the 4th, I mean, each element has an inverse. So we have checked off the inverses axiom. But there's one thing that's a little bit subtle that I didn't say, which is that when I have a function here, which is multiplication, when I write this notation from G cross G to G, if I want to apply that to H, then that actually needs to be, star needs to go from H cross H to H. In particular, what that means is if I multiply 2 elements in here and it lands somewhere outside, then it won't be a subgroup. So an example of a set that is not a subgroup, let's call it H prime. Let's say 1 x squared, x cubed, and x to the 4th. Now, if I multiply x squared and x cubed, then I will get x to the fifth. So the multiplication function is not a function from h cross h to h. It's a function from h cross h, and this value, x to the fifth, wants to be in h, but it's not. It's actually not contained in this set. There's no x to the fifth in here, so we have nonsense. So what we could say is that multiplication is not well defined, is the mathematician's way of saying that. So to make this more explicit and less subtle, what I'll do is, so we'll write a proposition, which is our characterization of what it means to be a subgroup. Subset, let's make this subset H is a subset G, where G is a group. G is a group. Parentheses. A subset is a subgroup if and only if the following three things happen. So I don't really need to write associativity, because I know that since I'm using the multiplication from my big set in my little set, so I'm not even going to write that down. That's always satisfied. So I'm going to write identity. If and only if, maybe I should write the following axioms hold. The identity axiom, the inverses axiom. That's another thing that actually the subgroup H prime does actually satisfy the inverses axiom. The inverse of x cubed is just itself. And what I'll call closure, which I'll write out explicitly. So for every A and B in H, A times B is also in H.